all of you to attend this webinar organized by the SAF RA partnership. It's the coordination of European research on industrial safety. For the meeting today, for the webinar today, we will have a presentation from Mr. Florian Part from the University of Boku in Austria. He is the coordinator of SafeLiBatt. So during the meeting today, during this webinar, we will have first some words about the SAF RA initiative so that you know all about the context of this partnership. Then we will have a presentation for about 30 minutes, 35 minutes from Florian Part. And then we have reserved time for question and answer about the result of this project, SafeLiBatt. So to start, some information about SAF RA. Many of you know already. This is a partnership with institution and funding organization that you can see on the screen on the slide. The institutions are from various countries, from Germany, Austria, France, Serbian, Spain, Basque Country, Italy, Finland, and Czech Republic. The story of SAF RA started in 2012 with the NERANET, a project aimed at coordinating the research investment in the field, in our case of industrial safety. And the vision that the partner have developed is to reinforce the competitiveness and the sustainability of the European industry thanks to improvement in safety, in good practice for safety and safety management. And the research that we would like to see is a research where we have various disciplines working together and interaction with the stakeholders. The SAF RA mission is to coordinate the research investment in Europe and encourage the cooperation between researchers from various countries and the scientific disciplines. Also create new perspective and opportunity for safety research to provide industry with forward-looking solutions to try to anticipate. Also share emerging societal concern, knowledge and research results on industrial safety thanks to the SAF RA symposium that is organized every year, and promote research on industrial safety as a competitive advantage and also a contribution to societal decision-making on innovative technology. So this is, in a nutshell, the mission of SAF RA, which has also value. The value are that safety is a keystone of competitiveness, sustainability, and social welfare. That openness, transparency, and objectivity is very important, and cooperation based on trust and fair partnership, respecting partners' interests and diversity, is also very, very important. So these are some quick information about the development of SAF RA and the vision, mission, value of SAF RA. What SAF RA has done over the last 14 years, 10 calls for projects have been published. You see some example of the calls on the right-hand side of the slide. Several calls were launched over the 14 years. The last one, which is still running, is about innovative solution and technology to improve safety of workers and emergency responders. In total, so far, 39 projects have been funded, and the main characteristic of the research cooperation in SAF RA is that it's quite lightweight, it's agile, with a project with a limited number of partners, and a budget also which is most of the time between 100 to 500 euro for project, typically of 2-3 years. And we are very proud that the time between the call and contract is less than 1 year. So it makes it a good solution to start cooperation within the SAF RA partnership and obtain quickly results. it's not so heavy compared to a European project funded by the European Commission, where you have a lot of paperwork and also a lot of competition. So I would like now, after this introduction, to give the floor to Florian Part from Boku University. So Florian, if you can turn on and your camera and take the control for your presentation. We are all very ready to hear about the result of the SafeLiBatt project.
Okay, good morning, everybody. So now it's an honor to present the results of my colleagues, because I was the coordinator and we had many PhD students working on that, and also other colleagues from France and Germany. And today you will hear the results of the SafeLiBatt project. Right, I will take just my laser pointer. Now it should work. Yes. You already see my slides, probably.
Yes, we see.
Okay, so laser point is not working. First, we'll start with a very generic thing, because nowadays we are always talking about value chains, but we have to change our minds, because we have to rethink everything, because we are mostly talking about value cycles. So today we are not talking about the first use of lithium-ion batteries, mostly about the second use, and there could also be a third use or a fourth use of the e-vehicle battery. And after this, after a certain capacity loss, the batteries will reach the end of life, and then we are talking about waste treatment and the end of life phase, in order to recycle the battery once again. I just present here some numbers. So you can see here the volume of batteries which reach the end of life is significantly growing. Also, by this, the possible second life applications also increases the volume. Some battery parts will be used for spare parts. This is this one, and the failure during the first use will decrease, because the technology just improves. What was the motivation of our SafeLiBatt project? So our, let's say, hypothesis to start was, when the capacity of a battery reach a loss of down to, let's say, 70%, the first life batteries can be replaced due to the warranty, secure and warranty reasons. And then the battery should not be, in our perspective in environmental sciences and sustainability, it should not be directly go to waste recycling, but it can be used for a second life. And today I will mostly talk about repurposing. Repurposing can be made for different applications, what you can see here. So we in our project, we focused on private applications, but the second life batteries can also be used for a bigger battery energy storage systems, like you can see here, or even for electric vehicle charging stations, or for the telecom base stations, or even for small mobile applications, such like forklifts, for example. But you can see already here some already commercialized systems for households, and once again for industrial applications. In our project, we started in January 20 and ended the project, finalized the project in May 24. So it was a big success and a long story because we had many things to do. The first work package was about abuse and thermal testing. The third one was about assessing the risks of possible or gas emissions. Then we had a work package on life cycle assessment. And to the end, we also performed some social economic impact assessments. So what you can see here is our team. So thanks to all of them and for the hard work. And it's really happy to see that most of them already PhDs and really made a nice career. What we did once again, our methods during our project. So we dismantled commercially available hybrid electric vehicles and battery electric vehicles. What you can see here, we obtained the cells because we did our testing on the cell level. I have to emphasize this. And then we did this aging and abuse testing. We collected all of the data, used the data for life cycle assessment and also for risk assessment. And based on our results, we involved also stakeholders. We organized stakeholder meetings and also stakeholder workshops. And then we could derive some measures for safety and standardizations. Now you will see the tests from the abuse and risk assessment tests. Before I talk about this, our start was, okay, we have to deep a little bit more into the degradation mechanisms. So once again, for most of you, it's probably not new, but for example, high temperature can lead to, say, growth or decomposition, or the fast decharging on fast charging can use to the binder decomposition and so on and so forth. So what you can see, the degradation mechanisms, which will lead to the end to the capacity loss of the batteries. What we did in our case, so once again, we had some cells. We obtained some cells from commercially available modules. And then we had 3 different types of cells. So one prismatic, a pouch, and other pouch tests with different nominal energy content between 19 watt hours and 290 watt hours to see if there are any differences in testing. Then we, or the BAM in this case, Robert did really a big job, a great job in cycling and calendric aging our cells in order to have different stages of health. There's different state of health. So and then we compared the cells at the beginning of life, so the new batteries with the, let's say, midlife. We set this at 80%, and then we simulated also end of life stages at SOH of at 60%. We were focusing Ineris, Arnaud and Robert from BAM. They focused on the safety parameters, onset temperature, which heat will be released and which gases will be emitted. And then we tested thermal and electrical stability, also the propagation and the gas emissions. So here you can see an overview of our aging and abuse test methods. So first we aged once again, and then we had different single tests where we applied different test setups. What you can see here, so this is very unique also in Europe, because they had their own customized test battery test centers. One is in France from Ineris. So here you can see the test chamber, and this is the test chamber with the BAM setup in Germany. Most systems, all of the systems are coupled to FDIR analysis for the gas emissions and also for GCMS, also to quantify the gas emissions. Here what you can see is different cell holders, which was a lot of work in order to customize the systems and in order to prepare or provide, let's say, reproducible test conditions. Then we had different thermal runaway situations, let's say it like this, triggered by ones by overcharging and the others by overheating. You can see already here the results on thermal and electric stability. What you can see first here on the left side is the temperature profiles and maximum temperatures during the abuse test. What you can see here are the differences between the beginning of life cells, and the yellow one is are the aged cells. What you can see here is that the thermal abuse lead to differences in the maximum temperature, but also in the onset temperature when the thermal runaway will be initiated. So what you can see here, there's a difference between the beginning of life and the second life. So the maximum temperature decreases in the case of second life batteries, but the onset temperature also decreases. So the thermal runaway will be triggered earlier. What you can see here in the middle is the results on the electric abuse tests. So the change in voltage. So the voltage before the first thermal reactions also goes down in this case, in the case of second life tests. So if you are interested in more detail, because the time is very limited today, I will just refer to our publications, which was luckily published last week. And then you can see here the results from gas analysis. So once again, we quantified the gas emissions using FDIR and H2 sensors, and also GCMS analysis for the trace gases, what you can see on the right side. But let's go back to the left side. So here you can see the differences in the cell types, and then what you can see. So there is not a significant, let's say it like this, I will conclude afterwards, difference in emitted gas volume, the relative one, which we normalized at 1 watt per hour, when we compare the new batteries with the second life batteries. What you can see here is also not a big difference in the behavior of the aged cells. These are the yellow bars once again with the new ones. So what we can see is always some gas emissions, DMC emissions and EMC emissions, they were almost the same when we compared first and the second life situations or simulated it. So then I already have to conclude these results from work package 2 and 3. So once again, the cells were after aging more sensitive to the thermal runaways, but the onset temperature also decreases. And also the overcharged tolerance increases. So a thermal runaway, this is what we conclude, happens possibly earlier. The maximum temperature also decreases, but the mitigation of thermal propagation is then in our case, I think, facilitated when we are talking about second life applications. And the volume of gases slightly increases. And the gas compositions, which I haven't shown you before, the overall composition of the gases, they remains very similar. So the risks, we conclude that the risk in terms of the toxic gases remains the same. And then we overall concluded that let's say the technical requirements in a battery energy storage systems are not the same as in a car, and therefore I think the use of the second life batteries should be safe for BESS, second life BESS applications. So this is what we conclude here. On the right hand, what you can see here, we also did a lot of, let's say, in-depth investigations after aging processes, and here you can see just some images from electron microscopy. Then what we recommend once again, so we can, let's say, achieve almost the same level of risks, but please take care for which, let's say, second life applications you will use your second life battery. This makes also a big differences regarding the technical requirements. And then for the, let's say, concerning regulatory and governance, we also really recommend, or we wish that we can continue our work in standardizing most of the test setups and harmonizing it, because we are competing with the worldwide market and we have to harmonize it maybe on the OECD level or on the UN level, what's still in progress. Because also BAM and ENERES, they are highly involved in these UN safety standards. And then we should also expand our standards, the test standards for second life. And then let's think once again about the state of safety, because most of us, we are talking about state of health, but state of healthy, once again, for this, the onset temperature is very important, for example. Yeah, and then I will also switch a little bit to life cycle assessment. What was and now I will show you the results of work package 4. And we also published many papers on that, which also made me very proud. And one work I will show you of this paper, it was about the environmental performance of the second life batteries, which we compared to the first life applications in order to quantify the, let's say, environmental benefits in terms of carbon footprints and carbon savings. And you can see the results here. And in this, in brief. And then I just also want to refer to other publications where I don't have so much time, because we also used our knowledge to derive some recommendations how to improve, for example, social life cycle assessments, which would be also the next step. Yeah, and here what we did during our ecological life cycle assessment, we call it LCA. It's often also known as product environmental footprinting, or the PEF method, which is also already recommended by the European Commissions when we are talking about the battery regulation. So this is also part of it. What we did in our study, so we compared once again the second and the first life batteries. Then we quantify it using or applying the PEF method. In this case, we also applied for life cycle impact analysis the recipe method. And then we just also developed some scenarios, because the LCA scenarios are also useful to show which components of the batteries can be reused and results in higher CO2 savings. And what we did, we focused on nickel, mangan, cobalt, oxide, cell chemistries. So let's see from the older generation, so NMC 111. We assume the same capacity to make it comparable. And then we differentiate the state between SOH 100% for the first life and 70% for the second life. Then we as the state of health is 100, you will need for the, let's say, demand of one household only 6 modules in order to provide this capacity of 14.4 kilowatt hours. When you have let's say already aged cells, you need more modules. And this also results in a higher demand of materials because you need more modules. And this is also reflected by a higher weight, what you can see here. And we consider this also for life cycle assessment, and then we compared it using the functional unit. It's 1 kilowatt hour of energy supplied to a German household, which is about, let's say, 9 kilowatt hours. And this corresponds to about 3,000 cycles of charging. And then I show you here the system boundaries on LCA. I do not want to bore you out. I just want to see, I just want to emphasize that even the method in life cycle assessment also needs to be standardized, because we have always different system boundaries, which are not always the same. And then you, for example, consider also material extraction, cell production, in the battery assembling, and so on and so forth. And in best case, you make you apply cradle to grave LCA. And then during the use phase, we also, of course, we considered aging processes. So they are relatively, let's say, simple formulas where you can where you consider the aging processes. And then we had this end of life phase. So once again, in our case, we focused on repurposing. What you can see here on the right hand, we have to adapt our system boundaries, because for simplification, we just excluded the first use phase in the ECAP battery. And then when you use this allocation approach, we call this allocation approach, you have to consider also where all of the environmental burdens and also the benefits, the expected ones, who will get the credits. And this is always an ongoing discussion. So who is the ones who has to take the burdens in terms of CO2 emissions? In this case, we allocated 25% of the emissions to the production phase. And then we also said that the rest will, for example, be allocated to the repurposer or the second life phase. And this is an ongoing discussion. We can discuss this later. But when we assumed these allocations, which was based on also some other literature data, we came to these results. And what you can see here, once again, we have different LCA impact categories, which we compared. So once again, this makes it a little bit complicated. So I think in most cases we are always interested in the global warming potential or in the climate change. And what you can see here in this graph, so it's a little bit complicated. In most of the scenarios, the second life batteries, let's say, have lead to results in environmental benefits. So what you can see here, the different, once again, life cycle impact categories. It's from metal depletion, so how much materials can be saved when we apply in the case of second life applications. And then, for example, we also had a scenario where we assumed that when we reuse, and this is the case 3, when we use the battery management system and the module casing, this can lead, of course, to the highest savings during an LCA. So now then I conclude in 14 of the out of 16 different impact categories, second life applications were better compared to the first life applications. We had two let's say negative ecotoxicological impacts because most of the recycling credits will be allocated in this case to the first life applications. So this makes life cycle assessment a little bit complicated and it's very hard to communicate, but I try to simplify it. But we also assumed, okay, we have to standardize the LCA, and then maybe instead of an allocation method, in order to consider the credits or the environmental burdens, we have to think about a so-called system expansion models, where we also integrate or consider in our system boundaries also the first life better. And this would be the next step, hopefully during our next projects. And then once again, we concluded, so the largest savings, or we found that the largest savings can be made in the case when we reuse not only the cells and the module, but also the BMS. This can decrease the CO2 impact by up to 44%. And this is really quite a lot. And then we can reduce the metal. We could use the material use. It's called, the impact category is called metal depletion, which is transferred to copper equivalents. In this case, we can use up to 61 of copper equivalents when we apply second life. So this was our take-home message in this case. And then I still have some time. I will also show you our results on the socio-economic impact assessment. This was the work mostly of our PhD student, Stephanie Brenner. She also did excellent work and published many things. So sorry, I've forgotten one publication which should be shown here, but I will share the links anyway. The first question was in our case, okay, we have now an, let's say, promising second life market, but where are the barriers for the market entry? Because, you know, there are not so many companies who are already commercially providing a second life, let's say, for example, battery energy storage systems, BESS. And Stephanie, she studied the framework conditions also, and once again, the barriers. And this work was also very interesting. She applied a so-called pestle analysis, where you consider also the political framework and also socio and economic aspects and so on and so forth. We conducted many expert interviews and also, once again, stakeholder workshops. And then we found which are the highest barriers. When we are talking about politics and regulations, so most of the entry barriers for second life applications are insufficient standardization and regulations. This is just needed because, and then we need also certifications. We are always talking about warranty, and the warranty is a big issue when we are talking about second life. And then the EU battery regulation, it currently focuses, let's say, mostly on recycling, but we should also, let's say, emphasize the potential of second life applications, and this should also be reflected maybe in the next amendment. Let's see what the European Union plans of the battery regulation. And then our BAM and Ineris colleagues, they are working already on the transport regulations, and some of our results were considered in this test series of the United Nations test series 38.3. And then they are also lacking second life testing requirements. So first life is addressed, but second life testing requirements should also be addressed. I just leave this here, and I will share my slides anyway after this talk. But here you can see a summary of the institutional frameworks. But I will talk now, because due to the limited time, about the economic market entry barriers. This was also very interesting because it's always about competitivity. Let's say it's just about costs. The costs for second life, because repurposing is costly, are very important, of course, because once again, you need many steps in handling and repurposing, and then you have to compete with first life batteries. And I have to be honest, you can't compete at the moment because first life batteries are too cheap, especially from outside from the Europe, from the EU. And maybe some incentives, this is just my own opinion, could help some second life, let's say, applicants. Then there are also another competitors, which was very interesting when we talked to the stakeholders. They are competing with the recyclers because the recyclers also wanna, of course, get some revenues of recycled or of collected and recycled lithium-ion batteries. And then Stephanie also identified high costs of expired warranties. And new warranties, it's also very costly. And then, we have to rethink even ownership models. Because most of the business and the ownership models focus on the first life. But based on the expert interviews, we found that performance indicators, especially for second life, are lacking. And then we need also some training of the workers because, safety is very important also, not only for us, but also mostly for the workers who have to do this repurposing and so on and so forth. And then once again, here you can find once again the framework conditions which would be needed and which incentives, some ideas. I just leave it as it is here now, and we'll go already to the social market entry barriers. So what we found is also the public acceptance needs to be increased, and I think hopefully also the webinar can also increase the acceptance of the second life applications. And then we have to communicate, especially also us scientists, to the broader public about the social impacts, because we also we tried to assess the social impacts from mining, extracting, and cobalt, let's say, mining to the use in second life applications, and this makes everything very complicated. But we have to communicate our results, and most of the concerns were for safety and the risks. Because most of the customers, they still have burning batteries in their minds, but I just we are engineers. We can I think handle the risks, and this is the good thing. Yeah, and then what we would be needed once again, we also have to ensure that all of the working conditions are fair, and this should be once again along the whole supply chain. But you know, the time changed, and because of the geopolitical conditions and situations, and but in a social life cycle assessment, for example, once again, we could even consider these working conditions. And then this is already the last market entry barriers, where about there's a lack of experimental data. And once again, yeah, it's also very hard to have access, for especially to the battery history and the data, because which is very important in turn, deriving some, let's say, safety aspects, such as the state of health and the state of safety of the battery. And it would be nice to have access to the battery history, but in most cases for the second life appliers, you don't have. You just have to pay, of course, a lot for this valuable data on battery aging and battery history. And then we also have to differentiate between the different battery chemistries and battery technologies. So yeah, NMC we need also more studies on LFP, for example, or on sodium batteries in the future. And then we also have to consider the safety of the residual risks, let's say it like this, what we did. And then for households, in this case, because we focus on households applications, maybe we need also other or additional safety requirements for second life applications, but we can discuss this at the end of my talk. And yeah, and then we always wish in science that we think about, let's say, design for repurposing or design for reuse, because this would facilitate, of course, repurposing in order, for example, to disassembly the battery pack and then to reassembly the modules, because on the cell level it's too, let's say, technically too complicated, and also it makes it also very costly in order to design the cells for second life applications. And then once again, here you can find the summary, and all of this you can read also in our nice publications here. They are already published online. And then this is really one of my last slides because I'm always over time. And I'm sorry for that. We identified for future or potential second life applicants some key performance indicators. So we ask regulators and customers, or in even the automotive industry, which KPIs are relevant for second life applications. And then we differentiate it between environmental, technical, and safety related KPIs and economic KPIs, of course. And then, yeah, and when we are talking about the environment, we always have our climate change in mind. So we were talking about CO2 savings, but also when we are talking about the circular economy, so the resource savings are always important, and we always have to compare it with first life applications. And then yeah, the recycling rate. So in this case is also important in terms of when we are talking about safety. Yeah, it's SOH is important, but also very important is the remaining useful lifetime. And this can be, let's say, predicted by some AI-driven aging methods when you have access once again to the battery history. This is the prerequisite for it. And then we were talking once again, or I was talking before, on state of safety. What about the onset temperature and so on and so forth, and the maximum temperature, and then costs. Yeah, this is always the same. But I just want to highlight this total cost of ownership concept. This would also be interesting and to calculate it. And there are some other projects already who did a lot of work on that. Yeah, and then I conclude this part. So once again, we identified, or Stephanie identified 12 preconditions and 12 KPIs, which are relevant and hopefully useful for second life applicants. And then we have some, we need more safety and testing standards. This also makes it more reliable and trustful for the customers, but we also need some incentives. Once again, we have to compete not only with the first life batteries, but also with the recyclers. And then what's really fair competition, and what's about warranty frameworks. This is also a big issue. And then, yeah, I just leave it as it is here. And I think we also need a rethinking in the business models. And I also highlight, once again, I guide you to the 9R strategies, because repurposing is not the only method which results in CO2 savings, but we also have to think about reuse, direct reuse, and also we also have to improve recycling and so on and so forth. And then, yeah, future work should be done to investigate especially X as a service business models. So we don't have to sell the modules, but we can sell the service, and this maybe is the future. And once again, the KPIs should be useful for that, and the business models which Stephanie mostly and her colleagues proposed should be validated, of course, in practice. So then, sorry for being late and talking very long, but we produced a lot of results, and I have to thank of course the team, because this was really great. It was really one of my best collaborations ever, and hopefully we can continue it. And then also for the funding, because without funding this would not be possible. And hopefully to the end we have a kind of system change, because we need some transformation towards circular economy and also for a sustainable battery industry. So thanks for your attention, and now I think there is some time for discussions.
Yes, thank you very much, Florian. It was very informative. We see a lot of results which are interesting in different directions. Very useful. I do not see so much question in the chat yet, but also participant can raise your hand. We have activated the microphone so that if you want to ask a question and not writing in the chat, you can ask your question directly to Florian. But I was looking at your recommendation, and you said you would like to have more certification, more regulation. Is it mainly for the state of safety, also to be able to characterize this state of safety, that you would like to have more standardized approach to also build the trust and remove some of the barrier for the societal acceptance to use second life batteries?
Yeah, exactly, because this would be very important. Once again, state of health. So, but there are already many regulations, but maybe they can be specified for second life purposes. And then state of health, state of safety would be just some additional, let's say, parameters like this onset temperature or the maximum temperatures, which should also be considered. Yeah, and then because this would mostly would be very important, such standards for warranty reasons, yeah, once again. And then, yeah, this should
how
makes it easier, hopefully. Yeah.
And in a nutshell, in few words, how you can explain the difference between state of health and state of safety? My understanding is that state of health is more for the performance and the capacity, and safety is more for the user. And even the user, I have in mind worker in a garage where they have to intervene on electric cars, or people who are doing some reconditioning of batteries after the second life. So after the battery will be used for a second life. So can you explain the main difference between health and the state of health, state of safety?
Exactly. You already explained it a little bit very well. Because when we are talking about state of safety, state of health, once again, it's just maybe on the performance of the battery. When we are talking about capacity loss and such things, and state of safety is mostly, we consider mostly, once again, possible risks during the use, the second use or the third use, and there you have to differentiate. So it really makes a big difference if you use, if you want to use a battery for second life, large scale BESS, compared, for example, to household applications. And their safety, we also have to consider the differences once again in possible gas emissions. And once again, the onset temperature when a thermal runaway can be triggered is also a very important parameter in our opinion. And this, yeah, but if you have further questions on this very technical thing, I really refer you to my colleagues from BAM and Ineris. They are really experts on that.
Yeah. Having in mind also the purpose of SAF RA to work on safety of worker, occupational health and safety, I have in mind also the result of your research for worker in a garage or in, as I said, in warehouse where you have some reconditioning or preparation of second, third life battery. What would be your recommendation for this worker? Do you have specific recommendation in terms of prevention, in terms of training, in terms of specific personal protective equipment or procedure for emergency as soon as a runaway start and you start looking at some fumes, smoke coming from a battery? From your experience with this research, on a practical point of view, what would be your recommendation for us?
So first of all, I think the safety measures are the same as for first life batteries. When you packing, for example, or assembling or reassembling some cells, yeah, every company has their own safety protocols and just follow that. And then when we are talking about end of life and also possible risks because of, let's say, thermal runaway and gas emissions, so there was a lot of work done, for example, by other projects also funded by SAF RA with regard to the first responders. Yeah, it's just, yeah, you have heavy equipment when you have some accidents, but accidents are very specific. But when you are handling with such second life modules, I just recommend follow the same safety safety
for
yeah
the life, yeah.
as for first life. And yeah, once again, for transportation we have these UN standards, so many standardization has already been worked out. And yeah, and it should it can be specified for second life applications, but the difference in our opinion is not very big. Yeah.
Okay. Thank you. I see a question in the chat from Heikki Koivula from Tukes, and she's referring to the waste and recycling of battery directive, I guess. So are you going to analyze more the competition from recycling, which is needed to fulfill the EU directive? So this is in the conversation, you have this comment and also reference to a European document.
Yes, very good question, because in my opinion, the battery regulation is very useful, and it really makes a lot of sense also when we have to improve the CO2 footprint of the battery along the whole life cycle. So the battery regulation also helps you, for example, in defining the functional unit of the life cycle assessment. I think for the life cycle assessment, once again, when all, let's say, battery producers would apply the PEF method, then you have fair conditions when you compare different, let's say, battery manufacturers. And for this, I think the next step would be to standardize and harmonize the LCA method for the European situation. And then, for example, you can compare, okay, a battery, when the manufacturer allows you or facilitates second use, then you have some CO2 credits, what we showed in our results. And these results should be documented, and this is also nice in the battery regulation, by the battery passport. But
it will create an incentive somehow, yes.
Yes, and this is also what I really believe is it could even be used, in my opinion, or it would be the basis for CO2 taxations. Because LCA is a reliable, robust method. Some data maybe is missing when we are talking about some life cycle inventory data is missing when we're talking about repurposing, but we can, rely on our PEF method and should just apply it and constantly, because technology improves. And then, maybe you will see if you produce many things in Europe, and then when you can reuse or some spare parts from some batteries, there's also a spare part in the second life market. And this can also be once again reflected in a battery passport or in a material passport or in a digital product passport and so on and so forth. But it's a lot of work, but we are, I think, in a progressive, yes. And
there is another question on this topic. Sorry, there is another question on this topic from Koivula Heikki. Any idea how to get spare parts from EV manufacturer to repair the EV batteries instead of replacing the fully functional battery pack due to a small dent in the bottom plate?
Also a very good question, because this would be anyway needed, I think, in the future. But I don't have so many insights in the company. And honestly, I have to interview first a company to say, okay, which spare parts for example, let's take the BMS. We were talking to some second life manufacturers. Let's say it like this. And they said, okay, the BMS, it's not damaged. You can directly reuse it and reprogram it. And that's the reason why we also derived or developed these scenarios in the LCA. And this, I think, and this should be facilitated when you have this design for disassembly and design for repurposing, because you know the screws and so on. Most of it's connected with binders and so on and so forth. It makes it not easy to obtain all of the spare parts and reuse it once again. But in a life cycle perspective or LCA perspective, it's obvious. It just results in many environmental benefits.
Yes, I see the point that if it is better designed, better prepared, then we can better reuse some modules, and that is a good point. So I think we are reaching the end of this webinar. I would like to thank you very much, Florian, for sharing these results, taking the time to share the results. It has been very useful. Thank you to all participants, and we will provide access to the replay and also to your slides. And if anyone has a question, I think they can contact you directly.
Yeah, also thank you for the invitation, and it's always nice to discuss our results with our colleagues from all over the world.
Thank you very much.
Welcome.
Goodbye, everyone. Bye-bye.
Goodbye.